Hello, this is Amin Sheikh, and I'll be doing Lab 5. So the purpose of this lab is to observe and model a barred magnet falling through a conductive non-ferrous tube. The barred magnet and the aluminum foil compose the system, while everything else is the surroundings. So what happens is that the barred magnet drops slowly through the aluminum tube due to a magnetic force acting upward. And as you can see here are the times for the experimental and computational. So some important principles is Newton's third law, which states that forces always come in pairs. Newton's second law, which states that the force is equal to the mass times acceleration. Faraday's law, which states that EMF induced in a coil is directly proportional to the rate of change of the magnetic flux through the coil. And Biot-Savart law, which states a constant current generates a circular magnetic field around it. So a quick look into the procedure is to drop a barred magnet north facing down through the aluminum foil tube. Then we did this 5 times and recorded the time it takes for the magnet to exit the tube, and we did it 5 times to determine the average time. So we assume that air resistance is negligible and that the barred magnet can be modeled as a magnetic dipole. So here's a look at our experiment. So here are our calculations, and as you can see, our average time was about 1.2 seconds. So for the computational model, we use Faraday's law to determine the EMF created by a changing magnetic flux to the ring. With the EMF, we divided it by the resistance to determine the current. Then with Biot-Savart's law, we determined the magnetic field experienced by the ring. And then later on, we determined the magnetic force of the magnet on the ring. Continuing on, we used Newton's third law and said that the magnitude of the force on the ring has to be equal to the magnitude of the force on the barred magnet that's falling down. And then with Newton's second law, we did a velocity update saying that the change in velocity is equal to F net divided by the mass, and thus we did the velocity and position update formulas. So here are our results. As you can see, inside the tube, the two forces are equal, while outside the tube, the gravitational force is greater than the magnetic force, as you can tell by the change in velocity being non-zero. So which color, red or blue, corresponds to clockwise current and counterclockwise current? Red is counterclockwise, while blue is clockwise. The counterclockwise current in this scenario corresponds to a magnetic moment with a plus y hat. And what happens if you flip the magnet around? Well, the time to fall remains the same, but the current directions change. So the difference between our computational and experimental results, as you can see, was that the computational time was slightly less, so the computational was faster. And if we accounted for air resistance, we probably would have increased computational accuracy slightly. So what does the plot shape tell us about forces acting on the magnet? Well, as previously mentioned, outside Fg is greater, while inside they're the same. Fg is equal to the magnetic force inside. Potential errors could be slightly inaccurate measurements, air resistance, and the bar magnet entering the tube with a non-zero velocity. So what if the resistivity of the conductor were reduced close to zero? Well, since I is equal to the EMF divided by R, a lesser resistivity would create a greater induced current. Thus, the bar magnet would experience a greater magnetic force, slowing it down inside the tube. What if holes or slots were cut into the tube? How would this affect the ring currents in the model? Well, the holes would essentially remove the rings or loops wherever the holes were, reducing the total number of loops and thus decreasing the magnetic force acting upon the magnet. Therefore, we could expect the baryon magnet to travel faster. That's it. Thank you so much.